About a week ago, we were looking at binomial distribution curves, sort of the probability distributions. If we flipped a coin 50 times, what would happen, or what was likely to happen, or somebody was likely to make 70% of their free throws, what were the likely outcomes? And we made probability distributions. The problem is that those, you could see the calculations became tedious because we had to figure out, if we want to say know the probability of getting more than 10 heads if we flip a coin 15 times, you had to add up a lot of the bins. Okay, each bar in the histogram had to be added on, and it could take a little while. So it's nicer in math when we can work with continuous functions instead of things that look like staircases. So this video is going to go introduce a smooth function that can often be used to approximate a binomial distribution called the normal distribution, or more commonly as the bell curve. So let's explore. Okay, so if this were a coin toss, okay, so we've looked at this code before. You can see we have n equals 5 with a probability of success of 0.5. So that's like a coin toss. If we toss a coin 5 times, this is the distribution of outcomes. It would be pretty easy to figure out what is the probability of getting 4 or 5 heads. But if instead of 5 flips, let's say I did 25 flips, and I wanted to know the probability of getting 15 or more heads, I start to have to add up a good number of boxes, all right, on this histogram in order to estimate what that probability is. And if this were went up to 100 flips, and I wanted to know the probability of getting more than 60 heads, I would have a lot of calculating to do. You can see the probability is low because most of the time we're below 60 on this graph, but we would need to calculate it by taking all the possibilities from 60 up to 100, and that would become pretty time consuming. So maybe there's a curve that we could use that could approximate this in a very smooth way. And we wouldn't have to deal with all of the steps. All right, so let's consider a curve. All right, so I'm going to start playing around with some functions. All right, to get this bell curve, it's basically a variation on EXP in MATLAB means e raised to the power. So it's a variation on e raised to the negative x squared power. And I'm using some quirky MATLAB syntax to get this to work. But if I go to graph it, you can see I have this big spike over here centered on 0. All right. Well, that spike is way too tall to represent the histogram of the probability distribution we have here. So I need to make it smaller. Well, what's a good way to make a function smaller? We can divide it by a number. Let's divide by 10 and see what happens. All right. So if I make this 1/10 as tall, well, that's looking a little bit better. It still looks a little bit tall. Let's try dividing by 15 and see what happens. Okay, too much, so let's try 12. That looks pretty good, about the right height. Okay, now I would like for my spike that's going to approximate the binomial distribution to move to the right. Well, we can see, well, the probability seems to be centered on 50 here, which is really just n times p. If I flip a coin 100 times with a 50% probability of success, on average, I would get 50 heads. So we would want to move this curve over by np. All right, so instead of squaring to move a curve over, I can take the input, and if I subtract the x value minus n times p, that's where the average is, that should move everything to the right by n times p. Let's see if that worked. It did. So now I have a curve that is right in the middle of my binomial distribution. The next thing I have to worry about, it's too skinny. I need to make it wider, all right? Well, how do you make something wider? Well, you take its input value and you divide by a number, and that will widen it out, okay? So we take the input to widen it, we'll divide by a number. We're going to divide after we square. We could divide by 4 before we do that, but it would just be a different number. So let's divide by 16 and see what happens. Oh, it made my little bell curve that I have here, the black curve, it made it wider, but not quite wide enough. So let's try another perfect square like 25 and see what happens. Okay, closer, but still not quite big enough. Maybe let's go up to 36 and see what happens. Oh, that's getting close to the curve that we would want, okay? So you can see by playing around with the variations of e raised to the negative x squared power, we can make this curve move around and drop off on both sides of the average and come pretty close to matching our binomial distribution. Right now, I was just using trial and error. I've already coded in the exact fit, okay, or the best fit. So let me, let's see, let's get rid of these comments here. And I'll graph it again. And you can see it's pre-programmed and it's a bit more complicated exactly how much I have to stretch it vertically and horizontally. But basically the way I was just playing around with it is the way this curve is fit. It's a fairly complicated derivation to get exactly what that curve is, but that seems to be a pretty good fit, okay? Now, that's a pretty good fit when I have 100, sample size of 100. Okay, so I've flipped my coin 100 times. Let's see if I drop this down to 10, is it as good of a fit? Okay, you can see that there are much larger corners sticking out. But the black line does kind of line up with the middle of those rectangles pretty nicely. So it's a pretty good approximation of our the probabilities for the binomial distribution, even with a pretty small number of data points. We go down to 5, we'll see, it doesn't fit it perfectly, but if you look at the middle of each one of those rectangles, the curve goes pretty much through the middle of the top of each rectangle. So it's a good approximation of what's going on, but it's a better approximation when this number gets larger, like 50. We can see there's not as much sticking out. So the curve matches the boxes much better, all right? Now, will this work if our binomial distribution is not a 50-50 distribution, where the probability of success is something more like 0.7? Let's see what that does. If you look closely, let me actually bring the number down. Let's go down to 25 instead. I'll make it more pronounced. You can see there's a little bit more sticking out from underneath of the black line to the right, okay? So the binomial distribution is not quite as good of a fit when it's skewed like this. Let's skew it even further. Let's go to a 0.9 for our probability of success. And you can see how it's sort of sticking out a bit more on the right, okay? So when the data is more skewed, this turns out to be, it doesn't work as well. So it seems like this, the black line is a better fit under 2 circumstances. When the probability is closer to 50-50, the black curve is a better approximation of the binomial distribution, although it wasn't terrible when I had 0.9 instead. It wasn't a terrible fit, but not a great fit. It's a better fit when I have an even chance of success or failure. And when the number of events gets larger, this curve fits better and better to the data, okay? And you can imagine if we had 5,000 coin tosses. That will actually crash my histogram in the program. But if we had 5,000 coin tosses, this you would not want to find individual probabilities for each outcome. And using this smooth curve might be very useful.